So electrical conductivity of semiconductors lie between metals and dielectrics. So semiconductors are actually one of the three categories of solids: semiconductors, insulators, and conductors. So say silicon and germanium are majorly used intrinsic semiconductors. Intrinsic semiconductor means pure semiconductor. Extrinsic means impure semiconductor. When we add dope into something, silicon or germanium, they become impure semiconductors or extrinsic semiconductor. They belong to fourth group in periodic table, silicon and germanium. They are called elemental semiconductors also. So at 0 Kelvin, that means minus 273 degrees centigrade, these elements are insulators, whereas at room temperature, they possess certain amount of conductivity. Pure silicon and germanium are intrinsic semiconductors. By adding a small quantity of either third group or fifth group elements as impurity into pure germanium or silicon, the electrical conductivity of the material increases. Okay, the impure semiconductor is called an extrinsic semiconductor. Intrinsic semiconductors, in the band theory of solids, the semiconductor has filled valency band and an empty conduction band at 0 Kelvin. You know, in semiconductors, we have valency band and then above conduction band will be there. Okay, at 0 Kelvin, you know what will be there? It has filled valency band and an empty conduction band. So when you supply some energy, what will happen? These valency band electrons will move from valency band to conduction band. So the gap between valency band and conduction band is called energy gap of semiconductor. Usually the gap between these valency band and conduction bands is actually 1 to 3 electron volts. It can lie in between 1 and 3 electron volts. At finite temperatures, greater than 0 Kelvin, the electrons get excited to the conduction band. Okay. An empty energy state in the valence band is known as hole. When an electron comes from valence band to conduction band, okay, there, wherever void of electron is there, that is called hole actually. Okay, thus at a finite temperature, electron-hole pairs are formed. In an intrinsic semiconductor, the number of electrons, conduction electrons, are equal to the number of holes. The electron or hole concentration is given by Ne is equal to Nh, that is equal to 2 into 2 pi kBt divided by h square whole power 3 by 2 into MEMH whole power 3 by 2 into exponential minus Eg by 2 kBt. Okay, usually it will be represented by this. We will be deriving it also. So Eg, energy gap, for silicon, it will be 1.11 electron volts. In case of germanium, it is 0.72 electron volts. Okay, pure semiconductors will have energy gap of this much. Germanium will have 0.72 electron volts, whereas silicon will have 1.11 electron volts. Me and Mh are mass of the electron and mass of the hole respectively. The electrons and holes are distributed among energy levels according to Fermi-Dirac distribution. You will be deriving it in quantum mechanics. Soon we will see that. F of E is equal to 1 by E power E minus EF by KBT plus 1. So, probability of finding the electron actually, okay, that is actually F of E. FH of E is equal to 1 minus F of E, because together it should come up to 1 actually. Probability of finding electron and hole should be 1. Together 1. EF is actually Fermi energy, and the probability of occupancy of this level is equal to half. Actually, in pure semiconductors, this Fermi level exactly lies at the center of the energy gap. What is energy gap? It is the gap between valency band and conduction band. So, the Fermi level lies exactly at the center in case of pure semiconductors like silicon and germanium. Okay, what is actually Fermi energy? It is the maximum energy attained by an electron at 0 Kelvin. That is called Fermi energy. Okay, an isolated silicon or germanium atom has 4 valency electrons. Okay, 4 valency electrons. Silicon and germanium crystallizes in diamond cubic lattice. Okay, it will have diamond cubic lattice. Each atom has a coordination number 4. Because 4 electrons, free electrons will be there. So 4 electrons will pair up with other silicon atoms, electrons, other 4 electrons. Thus, each atom has tetravalent bonding around them. At a finite temperature, some of the bonds can be broken and there are free electrons in the lattice. What will happen if you raise the temperature of the intrinsic semiconductor energy? What will happen? Then some of the bonds can be broken and electrons will be liberated in the lattice. A missing bond is recorded as hole actually. See, this is actually at 0 Kelvin, at absolute 0, how actually a silicon is bonded with other silicon atoms. You can see this silicon is contributing this. So this silicon, this electron, this one, and then this one and this one. So each silicon is contributing four electrons. So they are pairing up with other 4 electrons in the another atom. So like that, bonding will be formed. You can see here, this actually, this circle represents silicon atom actually. See how they are actually, this structure you can see here, how it is mentioned. Okay, here how hole formation will take place, we'll see. Here I already told you at some temperature, it is other than 0 Kelvin. So at finite temperatures, what will happen? Electrons will be freed up. So they are liberated, so that here electron here, it has moved from here to here. Okay, so there you can see the hole formation. Here also you can see, here it is electron is there, here hole is there. So that means electron is moved away from this position. Okay, at finite temperatures this will happen. So graphical representation is like this. Okay, it is conventional to plot actually E versus K plots for electrons and holes. Electrons and holes can be treated as particles with an effective mass m star or waves with the de Broglie wavelength. Okay, because we are treating them like, as particles. Okay, with an effective mass m star or waves with de Broglie wavelength. If it is a material particle, then it will have de Broglie wavelength according to quantum mechanics. Then E is equal to P square by 2m star. That is equal to P means what? H by lambda. So you substitute H by lambda here. What you get? H square by 8 pi square m star K square. Lambda is equal to H by P. That is K is equal to 2 pi by lambda. This is called wave vector. Lambda is material particle wavelength. H Planck's constant. P momentum of the particle. Thus, E versus K is a parabola. The curvature of this curve is related to the effective mass of the electrons and holes at the particular value of K. The effective mass is given by 1 by m star is equal to 4 pi square by h square into d square E by dk square. The population of electrons and holes is shown here actually. Here we represent like this. Okay, energy levels and then population. This is Fermi energy. Okay, this is valency band. This is conduction band. Okay, this is called wave vector. Here, EF, Fermi energy. A semiconductor acts like an insulator at sufficiently low temperatures. Okay, I already told you, semiconductor behaves more like an insulator rather than conductor. I already told you, at low temperature, it acts like insulator almost. The conductivity begins to increase with the increase of temperature. In semiconductors, the conductivity can be drastically. Who raised the hand? Hello, students. Who raised the hand? Hello. Who raised the hand? Tell me. Who raised the hand? Anything you want to know? Or simply you actually raised up? Fine. In semiconductors, the conductivity can be drastically changed by doping. Doping means adding small impurity to germanium or silicon. Then they become extrinsic semiconductors or impure semiconductors. Okay, a doped semiconductor is an extrinsic semiconductor. Okay, doping provides additional energy levels in the otherwise forbidden energy gap. What will happen when you dope with something else, third group or fifth group element to this fourth group elements? They create additional energy levels in the forbidden gap. Okay, additional energy levels. You can see here. Donor levels are close to conduction band, while the acceptor levels are near to valency band. This is valency band and this is conduction band. You can see here, because of doping, these many electrons are there. So, you can see at 0 Kelvin, electrons are like this. At T is equal to 50 Kelvin, what is happening? They are moving, jumping from valence band to conduction band. You can see here what is happening clearly. Okay, for insulators, the energy gap is much larger than those of semiconductors. Okay, I already told you, semiconductors will have energy gap in between 1 to 3 electron volts. Whereas, for insulators or dielectric materials, they'll have energy gap much larger than semiconductors. Okay, note also that the photons in the visible spectrum do not have sufficient energy to excite the valency electrons to the conduction band. Okay, arthamaitanda? Photons in the visible spectrum do not have sufficient energy to excite the valency electrons to the conduction band. Hence, diamond is transparent in visible light. So, diamond energy gap is greater than 6 electron volts. So, this much energy is not that easy to supply. Okay, to raise the valence electrons to conduction band. Okay. The metals have part.
Yeah.
The metals have partially filled bands. They have very high conductivity because of the very large number of electrons can participate in the current transport. Empty energy levels in the partially filled band allow the electrons to gain from the electric field. Unlike semiconductors, it is difficult to alter their conductivity. Okay, we'll come to extrinsic semiconductors in detail. The electrical and optical properties change on doping. What will happen when you add impurity to intrinsic semiconductor? They become extrinsic. What is called doping? You are adding impurity to the pure semiconductor. That is called doping. Doped semiconductor is extrinsic semiconductor. On doping with a trivalent atom, the four-fold coordination is no longer satisfied and a hole is formed. Okay, on account of missing bond. This is known as p-type semiconductor, and there are excess of holes. A pentavalent dopant atom is added to the pure semiconductor. Then what will happen? Pentavalent, right? 5 valency electrons. So what will happen if it pairs up with other 4 valent atom like silicon or germanium? 1 electron will be excess. Okay, 1 electron will be excess. Then what will happen? There are excess number of electrons. This type of semiconductor is known as N-type semiconductors. If majority charge carriers are holes, then it is called P-type semiconductor. If majority charge carriers are electrons, then it is called